One of our first topics is going to be states of matter, which I know you've done before. But when we're talking about states of matter, we're often going to refer to like the smallest particles of something. So even though that's really more of our Chapter 3 or Unit 3 material, we need to, of course, mention what those particles even are. What does that mean, the particles in something? So we have these two terms, atoms and molecules. An atom is the smallest particle of one, any guesses? Oh, good guess. Element. One element. And again, the list of the elements is all on the wall there, our periodic table of elements. An element can't be broken down into something different, a different property material. Like you have gold and you keep cutting gold in half, and you keep cutting gold in half. It's still gold, but that's because gold is an element, okay? Molecules, though, are the smallest particle of a compound, and compounds are made of more than one type of atom, more than one element. Perfect example of a compound you know is water. Now I keep cutting water in half, keep cutting water in half. It's still water until I get down to a molecule of water. If I wanted to break that apart somehow, I would no longer have water. I would be breaking into what component parts? There you go, hydrogen and oxygen, which are elements. So when we see pictures sometimes, you know, if it's just one atom, like in this case, you know, what is Al supposed to represent here? Aluminum. Then, well, how many aluminum atoms in this picture?
7 or 8.
Yeah, it looks like 8. They're all Al, all representing one element. How many molecules in this picture?
0. 1, 2, 3. Oh, 0.
None.
Good, 0, none. These aren't molecules. These are individual atoms of aluminum. So is aluminum an element or a compound? It's an element. Aluminum is up on the periodic table. All right, now we have this picture. We have some C's and some H's.
3.
How many atoms?
3. 12.
12. 3.
None.
15.
There ain't none. No, there's 3 little C's.
Who said 15?
3.
15.
15. How did 15?
How are there 15? Yes.
They're all atoms, but they're not.
Because the C in the middle counts as well. Every individual circle is simply representing an atom, including the C's, though. How many molecules?
3.
Good, 3. Those would be sort of your groups of atoms bonded together. So 3 molecules in this picture, 15 individual atoms. Is this an element or a compound? Good, this must be a compound. Okay, so when we're referring to the smallest particles in something, we will be talking about the atoms and molecules in that thing. So that's just a little bit of the gist of what we're talking about. Okay, so the states of matter, we're going to talk about solids, liquids, gases, and plasma. Of course, the big 3, the most common 3 on Earth, would be solids, liquids, and gases. And the terms we're going to use to define them are definite and indefinite. Definite, of course, just meaning set. You know, indefinite, not set, something I can easily change. So we'll see that explanation here. Okay, so you have this little chart. And I want to use the terms definite and indefinite to describe most of these. So the size of a solid. This pen. Is that set? Is it definite?
Yeah.
Yeah, absolutely. Shape. Does it matter where I put it? Is it going to have the same shape? Sure. Also definite. Particle movement. Okay, actually I don't want the words definite or indefinite here. So here's a pen. It is made up on its smallest level of atoms and molecules. Probably got these long plastic polymers. But they're still molecules, itty-bitty molecules. Are they moving around?
Probably not.
Yes. And I know that that seems weird, but yes. They are moving, although not very much. Okay, one molecule of plastic at the tip of my pen is not going to at a later time end up at the top of the pen. They're sort of set in place, but they do vibrate. They vibrate back and forth. And our particle spacing, you don't have to draw this many dots, but it's tightly packed. That's how we would define a solid. The particles in a solid are closer together than the other two. And in many cases, sort of in a pattern, maybe a crystalline structure, but often in a pattern, not random. So imagine I have, a glass of water. This one, liquid's sort of the one tricky one to figure out. I think the rest of these are pretty easy. What is indefinite, the size or the shape?
Shape.
The size.
Shape and size.
Who says size?
Shape.
Who says shape?
Mm-hmm.
All right, shape is correct. When I say size, maybe also think of volume.
Oh, yeah. Oh,
If I have 50 milliliters of water and I pour that on the floor, do I have more or less than 50 milliliters of water? Yeah, the same. I mean, all right, I realize there might be a drop left behind in the cup, but there's still 50 milliliters of water represented, whether on the floor or in my cup. But the shape is certainly not definite, because if I pour that water on the floor, well, now it's, puddle shaped.
the floor was hot and then it evaporated.
Okay, and then we get into our gas.
Like, freeze it, does it
Well,
change? Like,
mass, no.
or not map of size.
Water, yes. Water actually, well, all of them, yes. But water is unique in that it does expand when it freezes, whereas other things would get more condensed when they get colder and freeze. So liquid, so our particle movement, our molecules are now a little more random. There's not necessarily a pattern going on in a liquid. And of course, they can move around. So a molecule of water at the bottom of my cup could later be at the top of the cup. But they still stay together. There's still some sort of bonding energy between all the molecules, and they still stay together. So again, like I pour that water on the floor, it really does sort of stay in a little puddle together there on the floor. All right, and then gases, of course, these would be our indefinite, no set size, no set shape. If I have a helium balloon and I pop it, does the helium just stay there in balloon shape? No, of course, all that helium now spreads to fill this entire room. It takes the shape of the container it's in, whether it be a balloon container or a room container. So most spread out. What? You would need a lot. And we say those particles move quickly and freely, and they are not, attached or bonded in any way to any of the other gas particles. You can even think of this as, water if you wanted to. These could represent water molecules, or we could picture something that isn't. Maybe this is aluminum, individual atoms of aluminum. So as a solid, it's got its own definite size and shape. Maybe you could melt it down, turn it into a liquid, still would have a definite size, but what kind of shape? Indefinite, because it depends on the container it's in. And then if it was superheated, you could even turn that into a gas. And of course, those atoms would be the most spread apart, indefinite size, indefinite shape. You guys have that one. Do you know... Any guesses as to what that is?
That's a rock. That's a loaf of bread. Oh, it's a ham.
It's pork.
Pork tenderloin.
Yeah, that's what I get people to say a lot. It is not pork tenderloin. It is actually a chunk of pure, and this maybe will also help explain that a lot of the elements aren't found in pure form in nature, but this is actually sodium. NaCl, salt has sodium in it, but pure simply sodium, Na, sodium, is a really, really reactive metal. You have to store it in oil. It would react with the air, hence why it looks all kind of rusted around it. But it's actually super soft. So this person's cutting it with a knife, butter knife.
Isn't Poisonous when you.
Yeah, it's dangerous, it's poisonous. So they're actually melting it here. So you can see the particles moving around faster. And then sodium street lamps, especially ones that are kind of orange, yellow.
That was not annoying to me.
Liken easily, yeah.
Wait, so if you get a metal hot enough, it can turn into a gas?
Yeah.
Wait, so is
It would have to be pretty hot. Yeah.
boiling water?
You can also do the same with pressure changes too. Is boiling water a gas? Okay.
It turns into a gas.
You've got two issues with water there. Water can be a gas in its like superheated state of steam, or water can be a gas simply as water vapor in the air. Now steam would be really hot, dangerous to touch, but just humidity in general is water vapor in the air. So bear in mind, when we talk about water as a gas, we don't always necessarily mean it's steam. Does that make sense? Okay. All right, our kinetic theory. Do you know what the word kinetic means? It's a good science term.
Moving.
Moving, good. Motion. So this is our motion theory, kinetic theory. All matter is made of atoms and molecules that act like particles. Okay, got that already. Number 2, larger particles move slower. So what should that tell us about the particles of ketchup versus the particles of water? Water's got smaller, faster moving particles. Ketchup's got some really long molecules. And particles move faster given more heat. And that's partly why even the particles in a solid are moving, because there is always some heat. Do you know what the lack of heat is called? Or the coldest possible theoretical temperature?
Kelvin?
What Kelvin?
0.
0 Kelvin is called, starts absolute 0, good. And at absolute 0, that's where we'd have absolutely no movement whatsoever. But anything above absolute 0, no matter how cold it might seem to us, there's going to be some particle movement. So even in solids, even that desk you're sitting in right now that seems totally solid is made up of particles that are sort of vibrating in place.
For real?
For real. All right, changes in state. I'm sure you know a few of these already. But 2 of these probably are new. And I do want to add a couple synonyms, I guess. All right, if we're going from a gas to a liquid, for example, you leave your cold glass of sweet tea out on a hot summer day. What eventually happens to the outside of that glass? Yeah, there's condensation on the outside. It gets kind of wet. Maybe say the glass is sweating. Well, what's happening? Well, water vapor that was in the air already, that's simply around your sweet tea, is cooling off when it hits that cold glass and condensing. So that's condensation, is turning from a gas into a liquid. Now, vice versa, if I have liquid and I'm heating up a pot of water on the stove, I can eventually turn that water into steam, which can be called vaporization. That also happens sort of anyway. I mean, if you ever left a cup of water out, maybe on your bedside table, just left it there for a week, you're going to have less water, even if you didn't ever have a drink. Because of what? This process, but what's another word for that? Evaporation. So add that one in. Vaporization, evaporation. Oh, I missed my pen. And I want one more term that implies heat being added. Starts with a B. Boiling. Okay, so group these 3 sort of in your mind as liquid to gas. All right, solids, liquids, liquid to solid. Of course, you got melting and freezing. We know those. And two more, though, that you might not think of immediately, but are possible, given extreme pressure change, or maybe even extreme temperature change. Solid to gas or gas to solid. A solid to gas example would be like dry ice that you can buy in a grocery store. Yeah, it is carbon dioxide. It's just it's frozen carbon dioxide. Where do you commonly find carbon dioxide? Yeah.
Air. Plants.
Plants give off carbon dioxide. Plants inhale carbon dioxide. We give off carbon dioxide. So we are exhaling carbon dioxide all the time. But frozen carbon dioxide is called dry ice, and it never turns into a liquid. It's sort of like the steam or fog effect in theater or Halloween time. That's a perfect example of sublimation. Yeah?
If dry ice is frozen,
Yes?
and how does it burn you if it's cold and frozen?
So cold, hot.
It's just an extreme temperature change. Sometimes your body feels either super cold or super hot the same, simply as a painful burn. But yeah, it is cold. And that's a good point. So don't ever pick up dry ice like with your bare hands. Or eat it. All right, the vice versa of that. Gas to a solid, again, you'd need either extreme pressure change or temperature change. I don't know, one of those like end of the world movies, like this guy's like exhaling and his breath, his moisture is just like turning into ice and falling down. That could be an example of deposition, gas to a solid. So not common, but possible. Plasma, fourth state of matter, sort of a unique category. It's really a high energy state of matter. Our sun is sort of a big ball of plasma. And it's created when electrons are stripped from atoms. I know we haven't studied electrons yet. But that only really happens in these high energy states. It is the most common form of matter in the universe, though. Of course, if we're saying that the sun is a big ball of plasma, we'll think of how many stars are out there. That would be plasma. Yeah? Okay, plasma TVs are technically plasma, although not superheated. And they sort of achieve that with these pressurized little vacuum tubes and small amounts of matter to avoid the superheating. But it is technically plasma. Another example of plasma on Earth would be lightning. Yeah? No. Good guess, though. Good guess. On the verge. I mean, I would call Jell-O a solid. At just a certain temperature, then I, probably would turn into a liquid. Yeah.
What is like lava?
Lava would be a liquid. Liquid rock. Super hot rock. Okay. Whoa. Okay, I do want you to add this sentence in here. Here's our phase change graph, which we actually saw when we did our little graphing notes. So imagine you've got a chunk of ice with a thermometer frozen in the middle of it. You've stuck that chunk of ice in a pot, you stuck it on your stove, and you turned up the heat. Okay, what's obviously going to happen to the temperature? The temperature's simply going to go up. So this is sort of my graph here. Temperature's going up. It's still ice, but it's getting warmer and warmer and warmer. But then the temperature stops going up for a brief instant of time. Why would the temperature stop going up? What's happening then?
Melting.
It's melting. So some of that energy is diverted not into the temperature of the system, but that energy is going into sort of breaking apart these bonds between the solid particles, pulling them apart so now that they're liquids, and then the temperature will increase again. And then, of course, we'll reach the point where it's about to turn into steam, and so the temperature would actually not really go up for a little bit of time. That temperature is, again, that energy is being used to pull apart those bonds and turn the water into gas. All right, so energy is needed to break the attractive forces between particles when changing between states. So this is a common phase change, the phases being solid, liquid, gas.